Hello my friend and welcome in this new recording. This is going to be a continuation of the previous video I made, which was on an introduction on ray marching in native WebGPU. In this first video we were simply trying to display a couple of primitive shapes, a sphere and some kind of box. And today we will be extending that to try to display a terrain, and I can show you the result that we will achieve at the end of this kind of tutorial. I still want to make that some kind of tutorial. And here you go. You have this kind of terrain, and we still have the initial shapes in the model here. And I've been working to add the display of those mountains and everything around it. So yeah, I mean, my perspective, it's starting to look pretty cool, and it feels like this could be a usable terrain in the end. And we are going to go through all the steps that you actually need to, achieve this kind of result. And I guess at the end of the recording, we will also discuss some of the limitation and tips and tricks that I've been discovering on this way. So let's just get started now with the first step, and we'll move forward, and we'll probably have a full video with that. Let's go. Alright, so the first step to implement this terrain ray marching system was a modification in the simple application that we created for that. Simply changing, in fact, the shader file that we were going to use before. We were using this primitive file, and now we're using the terrain file. So ray marching terrain. So this is a file corresponding to this shader. What do we have now different compared to the previous one here? Here we have this mapping of the world where we have the sphere and round box, and then we calculate the normal and we do the ray marching using this map world function. Now in this new version, for the integration of the terrain part, it's pretty similar. We have the same content, except that we have those additional elements. So a terrain function, a terrain cast function, another function to calculate the normal for the terrain. But then we get back to the map the world and the ray marching here. What is different here is when you do the ray marching, the idea is first you're going to check on a given array if you have an intersection with your terrain, and if you have such an intersection, this is giving you the maximum distance from the camera that you should consider to try to find an object, because then it means that the object would be above the terrain, so it would be visible, and otherwise the object would be below the terrain, so you would display the terrain. So that's what we try to do here. We consider that by default we have a terrain distance, which is the maximum distance that we're going to use for trying to discover objects in the world. So we use that as an initial value, and then we perform this terrain cast function, which is going to update the terrain distance in case there is a terrain detected for this current fragment. And then we are going to continue with the regular processing. So we try to find any kind of object in the world. But what we use now for the distance, where is it exactly? Yeah, the total distance traveled. We're going to check that against what we consider to be the terrain distance, which could be the maximum distance or the actual terrain distance if there is a terrain. Because if we go past this distance, it means that we are below the terrain, so no actual object to display. So yeah, we do that, and then if we have, in case we find something above the terrain, we're going to return already with this path. Otherwise, we will reach this location. And so if we have some terrain to display, then we're going to use a fixed color here for the terrain, and again the same computation of the normal of the current location on the ground, if you want, to figure out what kind of lighting we have for this fragment. And if we really have anything, it means that we're looking at the sky, so we return this default color here. So where are those terrain elements coming from? This is a page I've been using as an initial reference, so from this guy, Inigo Gilas. So as I said already, you definitely want to check the work done by this person, because it's absolutely amazing. And that's a page. Yeah, this is it, right? Terrain Marching. In here you have some kind of introduction of how you're supposed to use a terrain marching system to display a terrain. And yes, this small drawing is interesting, because here it's actually showing you that this is different from what we've been using before with this sphere marching, because when you're doing your steps to find the terrain, in fact what is suggested here is to really use a constant step for your move forward until you actually get below the terrain location, the terrain altitude for your current location. Because if you're on this blue point, for instance, and you compute the terrain altitude for this point, you will find the altitude corresponding to this location. But then if you move to the yellow point here and you compute again the terrain altitude here, you will find the altitude above your current point altitude. So that's how you know that you are actually crossing the terrain. So yes, that's the initial implementation. And yeah, what is discussed then are small optimization that you can do. For instance, here you're going to interpolate between the altitude you get for the yellow point and the last blue point. And what else? There's another small, allow the error to be proportional to the distance. Okay, so dt here is going to be reduced progressively, I guess. No, it's going to be increased progressively, which in a sense is allowing you to travel a bit faster progressively, because the dt here is going to get bigger the bigger the distance t gets. So yes, that's the initial implementation I got, I think, so for the terrain cast function here. But yeah, I've been using a much bigger value for the maximum t value and a much smaller value for the minimal one. And the dt here is, it's not fixed, it's still proportional progressively. I guess, yes, the initial value here is not really important, because if t becomes bigger than 1, whoa, if it's smaller than 1, you actually have a lot of steps initially, so probably it would be good to use a minimal value of 1 here. Anyway, that's the terrain cast function. Then for the terrain normal computation, it's again a bit different from what we had been using before here for discovering the object and computing the normal for the object, because for the object part we were using this map the world, and we are calling that 6 times. And you compute the gradients in all the x, y, and z direction to get your normal. But you can actually improve a bit. In fact, we could probably use also this computation logic here for the normals computation of the object. But I didn't bother updating the corresponding code here. Anyway, for this part, it was also something I found in another article here. Oh yeah, I guess this is it. No, this is not it. This is the final result, but it's explained somewhere else. Let me try to find that. Okay, so the other article I had in mind is this one. So normal SDF, normal for an SDF. You can find that here, numerical normal for SDF. And if you go there, you have a lot of explanation on how you're supposed to compute the normals. And what we've been using before is this one. You compute the function f 6 times to get the normal. But there is this other option here, the tetrahedron technique, which means I think basically you're computing your normals on some kind of triangle pyramid shape. And you decompose those normals and you get kind of the same result as before, but with less calls to this function f, which technically can become extremely expensive. So it's always good to take. And so this is the tetrahedron implementation by default, but then you also have another version here, central differences for terrain, which is simplifying the function a bit, even if you still have those 4 calls. So I think basically this is the version that I'm using now in this first terrain experiment. Okay, so when you have that, all what you really need then is some kind of function to represent your terrain, and this is the one you're going to call in this terrain cast here, and it's going to give you the elevation corresponding to your ground location for any pixel. And this is what is represented in the Ray Marching terrain images here and here. For instance, this is a simple sinus multiplication, and it's building some kind of wave like that on your terrain, or you can have a completely flat terrain. And this function is what you're going to modify to provide different shapes in the end for your terrain. And in my case here, it's a simple sinus multiplication as shown in the article. So let's try to just run that to show you what it's looking like at this point. So you can see that if I move a bit up, I have those sinus waves, but I use a coefficient of 0.5, so it's a bit lower than what you might expect by default. And again, yeah, I think I've explained everything on this part. You do the lighting part then using the terrain normal, and that's basically it for the first step. Next, let's move to the second step. Oh, just one thing before we move to the second step I forgot to mention is that for the map the world function here, we're still using the SD sphere and SD round box, but you don't have those functions anymore because I have started to move them into additional files. So for instance, we have this Ray March primitives, which is Ray March here primitive, which is providing those 2 functions. And I have also updated the Ray Marching, I think I did, or I did not. Yes, I did, to include this primitives file, so you don't have the function defined here anymore either, those SD sphere and SD round box. Okay, so the second step that I took was to try to build this shader in a modular way. So we have updated the entry point here for the GLSL file, WGSL file, sorry. So we're using this Ray Marching file now, and if you open this one, you will see that it's just actually going to include a specific implementation, which is okay, because if you think about it, all those Ray Marching experiments, they are just all using this exact same input, so just using the camera, matrix, position, and so on. So it's fair to just come here and include different version of the file. So what we have here are the result of first the simple primitive display, for instance. So if you run that, why do you see this? Come on. Oh yeah, because I didn't rebuild the application. Let me just rebuild that very quickly. Okay, so now if you run it again, you should see only those two primitive shapes. And if you just select the terrain version 0, this was the result of the first step. So displaying a terrain with those simple sinus waves. And you indeed get this simple terrain display. And after that, we just will move to the Ray Marching terrain file here. And if you open this one now, you will see it's much smaller, because all we really have left is a terrain function itself, which is not changed. I'm using the same function for now, and the map the world function, which is going to describe all the objects that you have in this world on top of the terrain. And apart from that, we have this terrain marcher file, which is shared now. And again, this one is including a few different files, so we have all of them here now. And it's also providing a definition for this Ray March function. This definition here is the one which we described just before, because it's going to try to perform the terrain intersection and then try to see if there are some objects on top of this terrain, and otherwise you get to the shading part for the terrain or the sky display. And what do we have on top of that? The STD shaders file, this part is providing, in fact, all the shader entry points and the uniform definitions like this. And again, here we are including the primitives, providing so the SDF function for the sphere and the round box and so on. But you have here the vertex entry point and the fragment entry point, which is going to call your Ray March function. So that's it for the STD shaders. And then what do you have? You also have something that is specific to trying to render a terrain with the Ray March algorithm. So it's this file. This one will provide you with the terrain cast function, which again is the same that we described in the previous step, which is going to call a terrain func to figure out what is the altitude of any given pixel, I mean in a given location. And it's also defining the terrain, the get terrain normal method, which we discussed again before. So that's for the terrain. Apart from that, we have utilities. This one, I think it's, yeah, just providing a default normal function for all the object that you place on top of the terrain. And the very cool thing that I have discovered with WebGPU, I guess maybe it's the same with GLSL, in fact, maybe I didn't pay attention to that, is that the order of your function definitions really doesn't matter. So for instance, you have seen that in this terrain marcher, we are going to include terrain, and in terrain we have this terrain cast, which is going to call terrain func. But in fact, I'm only defining this terrain func after including everything. So all the other functions will be included here. And only after that you will see the terrain function definition. But it doesn't matter. When you're compiling the shader, the function is found, so it's well, linked or integrated into the terrain cast function properly. Same thing for the map the world, which is called directly in the Ray March function, I believe. Yes, here, and also in the normal function, which is in the utils part. It's going to be called here, and it will be found just fine. So the result of that, if we try to execute this now, it's going to be exactly the same thing. You still get the same kind of terrain, nothing more here, but in a modular way now. Okay, so let's move to the next step now. Alright, so the next step was to try to improve a little bit on the terrain function itself. And for that, I have introduced this version 2 now. The version 1 was still this simplified modular way with the sinus function terrain. And now for version 2, we are also now including this noise module. And in the terrain function, we're going to compute here value fractional Brownian motion noisy terrain. And this is coming from this page, I guess. So you get some initial details on what this really is. And you have here the basic idea of how you're going to build a FBM, so fractional Brownian motion. Starting from any kind of noise, because you have this noise function here. And the thing that I've been using myself for the start is this one, the value noise. And the value noise, you have a page here describing what it is, and some details here on how it's supposed to be computed. And basically, you have a main function here. And where do we have? Yeah, you have this shader implementation with a working value noise shader implementation. So this is what I've been using as a reference implementation. So I took basically this code, which I think is okay because this is MTI license, so should be OK. And starting from that, I have created this noise module. So you have that here, with a few changes, of course, to make it compatible with WebGPU. So you still have now the selection of what you're going to use for your hash function. It could be either integer hashing or float hashing. So we're using integer hashing for now. So you're taking this path, but otherwise this one should also be working fine. And then you have the actual noise function here, where you also get to choose what kind of interpolation you want to provide. And I'm using the squinting interpolation currently. And that part is basically the same thing as in the shader file here. It's just that I renamed the function to value noise derivative, because maybe later I'm going to add other functions like gradient noise derivative, simplex noise, and so on. And okay, this part is not relevant for us. Then on top of that, I have just added this value FBM function, which is the implementation of this. Well, not quite exactly like that, because as explained here you have the power function, which you can avoid, in fact, using this implementation instead. And okay, so this is basically all you need to define your noise. And after that, I could start using this to build the terrain. So in the terrain function, I just use this value fpm call with a given location. The one value here is the Hurst coefficient, so 1 is default, I would say. And you can also specify the number of octaves that you want to perform doing the accumulation here. Okay. All right. And I guess this is all we really have modified actually in this version. And now we can try to run that. And be ready. Ta-da! You probably don't see anything right here because yeah, I didn't start moving, but here you go. If you start moving and you look at the number of frames that we get, it's a disaster, a complete disaster. It's extremely slow. So I was pretty disappointed when I've tried that because if you go on Shader Toy, in fact, you will see that you have a few different examples that are working pretty fine. If you check, for instance, this one for elevated. Okay, I have the application running in the background, so that's not good. Let's just, yeah, it's going to kill everything. Come on. So let's kill this one. So here you're achieving a very nice terrain and the performance is very high. So if you put that in full screen, it's still working just fine. And I would expect this kind of performances, but no, definitely not the case. Whoops, no, not what I wanted to do. And the reason for that, I believe, is in this version, I'm using this terrain function, and I'm still using what I have in the terrain marcher here to, no, not the terrain marcher, the terrain itself, to perform this terrain casting, which is using not fixed, but almost fixed, not very changing step when you move forward on your race. So you have a lot of steps to take for every single fragment just to figure out where is your location where you have an intersection with the terrain, if you have an intersection with terrain. And then you also use this function again to compute the normals of the terrain. So it's very, very expensive for every single fragment. So too expensive, in fact, and it's just killing your frame rate. So you can't do it this way. But if you check actually what is done in the elevated version, here you can see that, well, I think the key element here is to consider using different version for your terrain. You can have a high resolution terrain, which, I mean, a function for high resolution terrain function, which is going to compute a high resolution elevation value for each point on the ground, but you're going to use that only when it comes to computing normals for this point. And then you also have a medium resolution terrain here and a low resolution terrain. I think the low resolution terrain is used only for positioning the camera, so we don't really need to care about it. But then the medium resolution is what is used to figure out what is the location of your fragments in the world. So this is already reducing the number of steps that you have, the number of octaves that you are accumulating to figure out what is the elevation, which is good to take. But here you see it's already at 9, and in my case I was just at 8. So here using only 8, but it was still way too much, so not good enough. The other part on top of that, I think, or the key part, is how you compute the terrain intersection, in fact, because the algorithm which is used here is pretty different from what we're using in the default version. Because here you see that first you only have 300 iterations, while in my case, in my terrain marcher, terrain cast here, I'm starting with a step of 0.1. I mean, maybe this is really it, because if you have this and you multiply dt by that, I mean, it makes sense that it's going to slow down everything terribly. So let's just try to start at minimal value 1. Maybe that's making a difference. Well, it's helping a little bit, but still not that much. And if you get close to the terrain, you're going to, yeah. Oh, that's funny. Very nice effect. Okay, what did I change? Yeah, value 1 here. Let's get back. So that's not good, but this is not good either. And the fact that basically the step yeah, you're just going to move forward, but by a step that is not really, well, going forward fast enough, basically. So that's not good. And what is done here is different, because what you do is you first compute the terrain elevation at your current point, and you also consider what is your current elevation for your point yourself. So if the terrain is way under you, you get elevation above ground, which is pretty high, which is this h value. So it means that if you are very high in the sky, your camera is very high in the sky, and the terrain is very far away, the altitude value that you will get here is pretty high. And then, in fact, this is what you're going to use to move forward. So you take only part of this elevation above ground value, so 0.4 times this value, and you use that to figure out what is going to be your movement forward. It's a bit some kind of imprecise, heuristic. You're not really sure that you're really going to get at a location which is still above the ground, but it seems that that's basically working, so it's fair, and it's allowing you to move much faster than using a step that is only slowly increasing. And I think this part is really the key part, making a difference. So yeah, I think what I'm actually explaining here is how I've been fixing this issue in the next iteration. So let's just try to move to the next iteration version. So the next iteration was actually the last one, the introduction of this version 3. And if we have a look at what we're doing on this one, things are getting slightly more complicated, because I'm still using this terrain marcher file, but now I am providing this terrain cast function definition. So I am defining this to be my terrain cast, and then I have this function defined after. What's happening now is in the terrain file, the terrain cast here, well, no, it's not here, it's on the terrain marcher. In the Ray March function, we have this now. If it's not defined, then by default we're going to use this function, terrain cast. But if it's defined before you include this module, then of course you don't get to this point. And that is the function name that you're going to use to get your terrain intersection. I also modify a little bit prototype of the function, because then now you can pass the minimum and maximum value here, but I'm not really using that because the value are still fixed for now. You could improve a little bit on the ray march function, I guess. I mean, improve further by making this max distance a dynamic value somehow. And in fact, I think this is what is done here, because when it's calling raycast, you have the max value provided here, and this is updated somewhere. I guess something like that. But yeah, I'm not quite sure to understand what this code is doing exactly, so didn't really bother to focus on that. As a first step, you basically don't need to do this, I guess. And so we have this custom implementation of the terrain cast now. And this one is doing the smaller number of iteration, as I mentioned before, as shown here. You use only 300 iteration, and I think that's the value I use by default here. And more importantly, you're going to compute the elevation above ground value and use that to move forward way faster than you would do otherwise. But then the idea is still the same. When you get close enough to wait a minute, absolute value of h smaller than okay, never mind. So you have your terrain cast here, and I don't know, this is bothering me. Well, no. Absolute value of h is a measure of the error, if you want, between your point altitude on your ray and the actual ground altitude. And all what you're saying here is this error should be small, but it should be proportional to the distance that you have traveled from the camera. So if you're very close to the camera, the error should be smaller. If you're far away from the camera, the error can become bigger, and it would still be acceptable. That's it. Okay, so we have the terrain cast updated. The terrain function also yeah, in the terrain cast, my terrain cast, I'm using a dedicated function here, a low resolution version of it. But low resolution is still using 9 octaves, which is pretty large already. And this is the one we use for figuring out what is the position of the fragment in the world. And then for this one, the high resolution version is the one we're going to use to compute the normal at this position. What do we have? Oh, also something else I've noticed is again in the elevated version, the computation of the normal for the terrain, where is that? Where is it? Oh, calc normal. The computation of the normal here is made depending on the distance of the point to the camera, which makes sense because if you don't do that, I mean, I can show you, if you don't do that, let's say you don't use t here, or even better, you just, well, no, you can just not use t. So if you do it this way, what you will notice is in the back here, you have this kind of noisy display because normal is getting unstable, basically. And in fact, you still have that pretty close to the camera here. But now, if you activate this part, so when you use a normal, you're basically reducing the resolution used for computing the normal when you get far away from the camera. And this is helping to stabilize the computation that you and the result of the computation, so you don't have so much noise anymore on those normals. So definitely something you need to do. And this is a function that we're using now in the get terrain color. And get terrain color is another addition that I have. So we have this get terrain color definition. And if you go in the terrain marcher with the ray march, you have this custom part. In case you have an intersection with a terrain but you don't have any object, then you check if you have this get terrain color defined. If it's the case, you are going to use this function name to compute the color that you want for this position. Otherwise, we have a simple default computation here. And the function we have implemented for that is shading your current pixel with a bit more advanced element. So I was starting to try to mimic and copy actually a bit what is available in this shader. I know I should not really copy that, but yeah, I mean, I've just used the logic here as a starting point, I guess. So the idea is really you try to figure out what is a rock color, and you try to mix that then with two different layer of green, in fact. And I feel, yeah, it's displaying much better on this side than what I have myself, but never mind. So you start with some two rock colors. I'll use those two. They are acceptable even if the color is not so great. And then you do some kind of mixing. It's just kind of random mixing basically. And then you are going to use a normal here to figure out if you can mix your rock color with the grace color, assuming the normal is mostly pointing up. And if it's really flat like here, then you're using another color again, which is some kind of a greenish also, I guess, or something like that anyway. And on top of that, you also have the part where you use the snow color. Again, I have to tweak a little bit the scale here because I'm not using the same scale as done by Inigo, but yeah, it's working if I use a very small scale. And after that, for the lighting part itself, I decided to keep the very simple lighting that I was using so far, because in the example here it's getting much more complicated. But again, I'm not sure to understand all the details, so not really. I mean, the results are better, of course, and you also have those shading effect which are better, so that's great. But for a small experiment like that, I don't feel that I really need to go this far. And anyway, using this simple lighting system, as you have seen, it's not too bad already, apart from if you turn on this side, you see that everything is pretty dark. But if you look this way, it's not too bad. And that's basically it for the result that we got for this initial implementation of a terrain with fractional Brownian motion. And that's pretty cool if you ask me. But there is still a significant issue, which is this one. If you increase the size of your screen, you are actually increasing the number of fragments that you want to compute. And if you do that, look at the frame rate here, it's again going down. And if you move around, it's a bit jerky, so not very good. So again, you're reaching a point where the computations that you're doing for every fragment are extremely expensive. And I have here on this computer a 3090, so RTX 3090, which is a pretty good GPU normally, and it's already killing this GPU. So in the end, I feel that the idea of performing ray marching is interesting, but it's still not something I would like to use as is for a game or something like that, because it's still way too expensive, I think. But at least it's giving me a few ideas, and I'm thinking maybe I have a way to kind of integrate this kind of noisy terrain computation into ProLAN, in which case the performances should be much better. So that's probably going to be for another step. And yeah, if you want to experiment further with ray marching, maybe you can find better way to optimize the rendering anyway. So, again, very long recording. Sorry about that, but yeah, thanks for watching. And if you have any question and I think I can help on anything, again, let me know in the comments. And otherwise, have a nice day. Happy coding on your side, and see you next time. Bye bye.